All right. Okay, we're gonna start. If you guys haven't already, make sure to sign in. So today is going to be our second ML Monday lecture. We're going to be lecturing on linear regression. All right. So introductions, I'm Alvin, I'm the education lead. I was the one who did the lecture last week, and I have other ML lecturers who are helping me out throughout this lecture series. Unfortunately, some of them were not able to make it today. But yeah. So some administrative information. So from our lecture last week, we have uploaded the slides and the YouTube stream. So both of these are available on our link tree. So I know some of you guys are new to the lecture today. So make sure you guys check those out on our link tree to get up to date if you want to. Some feedback that we've gotten since that section or since that lecture is about the difficulty of concepts. So of course, this is a beginner machine learning course. But it is machine learning, so expect that there will be new concepts and material, and that will be common, right? Especially some math maybe you guys haven't seen before, and that's like completely all right. If you don't understand the math, that's completely fine. Some of the notation might be really new and you guys don't have experience with it. All I would say is that you guys try to take the time to go through it on your own later on, especially if you don't understand it during the middle of the lecture. And there's some prerequisite knowledge, obviously, that is required, but we're going to kind of explain it as we go, and so we might skim over it. So if you have any questions, please make sure you ask. Just raise your hand in the middle of the lecture, and I'll get to you as quickly as I can. And always feel free to look up the material on your own. If something at the end of the lecture, you're confused about something, and you want to know more about it, I definitely encourage you to search it up online, see what you can figure out. We also have a feedback question. I'm sure that some of you guys have seen in the sign-in sheet, so if you guys want to give us some feedback, that'd be greatly appreciated. Some people also had questions for me from the previous lecture, and I just kind of wanted to emphasize some pitfalls of machine learning. Some people were having some ideas of how to use machine learning. So machine learning is a great way to predict things using data that you have, but is not extremely good at analyzing the world and understanding how it works, right? So for example, physics, machine learning is not very good at knowing what's going on. It might be able to find a pattern that works for certain things, but it's very bad at understanding what's going on. And even in the real world, let's say you try to predict something like obesity percentage, right? Based on health factors. Those health factors change over time, right? So you might train your machine learning model, but maybe in a year or two, right, it's kind of lost its purpose. It's kind of, the data has shifted, right? And so you don't really have a good model that represents that. So I just want you guys to be cautious. Machine learning is very good for some problems, but for some other problems, it kind of fails quite easily, and you have to be aware of that. So review of our previous lecture. Just as a question, has anybody been to the previous lecture here? Raise your hands if you have. All right. Does anybody want to kind of give a brief overview of the previous lecture and what we talked about for the people who are new here? Yes?
I remember some of it was just like the general overview of machine learning, how you can overfit by training it incorrectly.
Yeah.
Only looking at training data instead of having separate data for testing.
Yeah, definitely. Splitting your testing data and overview of AI and machine learning. Is there anything anybody else wants to add? Give the new people an idea of what we talked about last week. Yes?
Remember we talked about the loss function?
Yes, we talked about a loss function. Good. Do you remember anything specific about that loss function?
I think it used an average formula of some kind, average of the correctness, I think?
Yes, exactly. So we were, the loss function we introduced was the mean absolute error, right? Which is the, basically the distance from how far our model was from the true values, right? Anybody else have anything else they want to add? No? All right. Yeah. So review of the previous lecture. Essentially what we were talking about is the kind of overview of what is artificial intelligence, what is machine learning, right? And how it gets used, right? So we define machine learning very broadly as the theory and development of computer systems that basically mimics or does tasks that require human intelligence. So obviously this is a very broad and subjective definition. And what most people consider to be artificial intelligence is actually based on how normalized it is and how understood it is, right? So there's a lot of things in the past that used to be considered the pinnacle of artificial intelligence, right? You have speech to text, text recognition, face detection. Really in the past, this was considered really high edge, brand new AI, right? Nowadays, if you like scanned a paper using your phone and you converted it to a PDF and you weren't able to get the words off of that scanned paper, you might be like, this is, not the best scanner, right? So I don't know if you would really consider that to be AI anymore, but it really depends. And it's good to note that this does not really apply to machine learning due to kind of the definition of machine learning, right? And that brings us to it. So machine learning at its core is an optimization problem, right? The algorithm learns from data to make certain predictions, right? And the algorithm itself does not dictate how our model makes the predictions. And we can conceptualize each machine learning model really as a function, right? F of theta of x, where the parameters theta basically define the model that we have created, right? And you pass in the input and you get out an output, right? That you want to closely resemble what is actually happening in your data. And so what we try to do is we try to find the best function, f theta of x, right? And how we consider to be the best function is we then define a loss function, right? Which measures the error from the true target value. And I put error in quotations here because the error that we're usually measuring is very different from error that you might measure in other sciences, right? It's more of an abstract version, right? And your error can take on many types of forms. And that's why I put it there in brackets. So training a model means finding the best parameters, right? Theta to minimize the loss function. And in this lecture, we're going to be talking about linear regression, which is one way that you can use to find the best parameters for a very specific kind of model, which is a linear model. And of course, we have the alternate view of machine learning as a pipeline, right? That you have certain steps you can take in the machine learning process to try and solve a problem. And that hopefully, if you follow the steps properly enough, you end up with a good solution to your problem. So that's just a little bit of the review. So there's a few things I want to kind of formalize before we actually dive into linear regression. The first is loss functions, right? So we introduced them last class, but there's a few more things I want to add to it, right? So, right, we define the loss function as a function that measures, technically how far off our model's predictions are from the true values in the data set. It takes in our parameters, and it returns the error of our model as an output, right? And so what we actually want is we want our loss functions to be convex, continuous, and differentiable. And so I have the definitions for convex, continuous, and differentiable. Continuous and differentiable you guys might be familiar with from calculus, right? And convex is probably something that maybe you guys are not so familiar with. So basically in layman's terms, convex means, right, that for a function, any straight line drawn between 2 points on the function lies entirely above that function, right? So you can see here, on the graph right here, the equation that you need to satisfy to be considered convex, and then to be considered strictly convex, you just get rid of that. You make it a strict inequality instead of an equal to inequality, right? So it's actually a very good question as to why you need a convex function for your loss function. Does anyone have any idea why your function, your loss function, needs to be convex, right? Does anybody have an idea? Yeah, you in the back.
So you can find the minimum point?
You can find the minimum point, yep. So that's basically the intuition here, right? If you draw any straight line from 2 points on the function and the line is always above the function, essentially that guarantees that your minimum point is going to be the global minimum of that function, right? And so we need it to be continuous and differentiable because if you remember from calculus, if you have a function and you're trying to find the minimum of that function, well, obviously, you're going to need to take derivatives to find the point where the slope equals 0, right? Because you don't want it to be decreasing anymore when it's at this global minimum. The slope should be 0, right? So the next thing I want to formalize is this idea of hypothesis classes, right? So we said before that each model can be seen as a function, right? You take in the input and you output something that you want to be close to the data you provided, and the parameters theta define your model, right? But there are actually a lot of different functions, right, that can be defined by different parameters, right? And so the idea of a hypothesis class is kind of to limit ourselves to the types of functions that we are looking for, right? So the type of function we choose usually represents the architecture or model that we want to use, right? So 2 examples that we're going to be looking at in this lecture series is linear regression and logistic regression, right? And so we define the hypothesis class as the sets of all possible functions that a learning algorithm can explore to find the best fit for a given problem. And if you guys don't know the notation, you can ask me about it right now. But it's basically just essentially what we're saying is we're defining a set f of theta where theta is an element of big theta, and big theta is just the parameters that we're looking for, right? The type of parameters that we're looking for. And usually, in many instances, big theta will just be the set of real numbers as well, right? So you guys remember from our previous lecture, we defined kind of a housing price estimator or predictor, right? Where it took in two features, right? The square footage of the house and something else that I forgot. And it basically maps it with some weights and gives you the price of the house back, right? So for us in that housing price estimator, our hypothesis class, right, would be the set of functions f theta, x1, x2, right? And it basically takes them in, has those outputs, right? Where our weights, which is theta, right, is an element of the real numbers, right? So you can see how we got our hypothesis class pretty easily for our housing estimator from the last lecture, right? Right. So this is the set of functions we're searching in. And for convenience, we usually define the hypothesis class to be constrained to one model. Technically, you could have multiple models in your hypothesis class, but it just makes it more convenient for us to talk about. And the point of a hypothesis class is to constrain us, right? We don't want to look for a large amount of functions. We want to look for specific amount of functions, and a hypothesis class constrains us to where we can easily search for those functions, right? So often what happens is that our hypothesis class imposes structural assumptions on the data. And this is really important to note because when you choose a model, these structural assumptions in the data have a very strong, basically they have a strong effect in how your model performs, right? So this actually ties into what we call bias and variance, right? So I'll explain a little bit. So bias and variance are essentially two types of errors that you have in your machine learning model. Bias is the error introduced by having incorrect assumptions in your model, essentially. And what that means is that we're making incorrect structural assumptions about what is happening in the data. So our model is not able to capture the true relationship between the inputs and the outputs. So, right, as you remember, we had that housing predictor, and we assumed that there was linear weights, right, that map the square footage and the other feature we had to the actual house price. But we might not know if there's a true linear relationship, right? The data we looked at, we plotted it, and it looked pretty linear, but maybe later, actually, when you go further down the square footage, it actually shows that maybe it's an exponential or, some type of polynomial type of relationship between the inputs and the outputs, at which point our model would fail because our model basically assumes that there is a linear relationship in the data, right? So another example that we have here, it's not the best example, right? So suppose you're trying to predict kinetic energy by providing a linear regression model, mass and velocity, right? Well, mass and velocity of the kinetic energy, if you remember, the equation is 1/2 mv squared, right? So there's no weights that we can provide that gives a linear relationship between the mass and velocity to the kinetic energy, right? Even with infinite data, our model would consistently make wrong predictions because the model is making incorrect assumptions about what is happening in the structure of the data, right? And so what we usually say is that high bias means your model is underfitting, that your model is too simple to understand what's actually happening in the relationship. So the other side of the coin to this is variance, right? So variance is introduced by the model's sensitivity to the training data. So what do we mean by this? What we mean is that if you were to train the exact same model with the same parameters on slightly different data sets, right, that your model would actually have very different outputs because your model is too sensitive to the training data that you're providing it, right? And so high variance means, right, that the model's predictions would vary too greatly if trained on slightly different data. So for example, going back to the housing thing we always do, if we use a deep neural network for our house price, maybe we would find that as we swapped out even a few rows of our data set, that our neural network would actually have large changes in how it's predicting on unseen data, right? And so that's not the best because high variance essentially means that it's not able to capture, it's too sensitive to essentially what would be noise in the data, right? Your data will never be perfect, right? And if your model is too sensitive, if it's always trying to look for the best pattern then it might actually end up being a bad model, right? So we say that high variance equals overfitting, right? That the model is looking for patterns that essentially don't exist in the data because it's considered too flexible, right? So this essentially leads us to the bias and variance trade-off, right? So we have the error introduced by having incorrect assumptions in the model, and we have error in our machine learning model introduced by the model's sensitivity to the training data, right? So if anybody looking at these graphs, could anybody give me the answers to what would be low bias, low variance, high bias, high variance in these graphs here? Does anybody know? Yes.
High bias would be A and B because it's like underfitting.
Yeah, high bias would be A and B because it would be underfitting. Can you explain a little bit more about why it's underfitting here?
Yeah, so it's assuming just like a linear trend, but it's
Yeah.
really like D, it's more quadratic.
Yeah.
C would be variance because it's just following the data that it's been trained on. But like if it introduced anything new, then the pattern in C would probably not be like generalizable.
Yeah. Yeah. Does anybody want to provide like more specifics on what A and B is, like low bias, high variance, low bias, low variance? Does anybody? You guys can take a little bit more time to look at it. All right. So yeah, essentially what you said was correct, right? That A and B are high bias, essentially because, right, they have a straight line, and they're assuming that they can make a straight line that fits this data. But as we can see, it actually has some sort of like curved component, right? So when we're trying to use that straight line to predict the values, we actually realize that is not able to it's not able to capture the true relationship between the inputs and the outputs, right? And the bottom row is high variance, right? Because, or not high variance, sorry. The bottom is, let me see. C is high variance because essentially what's happening is it's too sensitive to the noise in the data, right? So you can see how it's kind of jumping between those points. So if we were to change any of those points, it would probably start jumping to them too. And so that's how we would get essentially a very different amount of data, or that our model would make very different predictions, right? So A would probably be the high bias, high variance. B would probably be the high bias, low variance. C would be the low bias, high variance, and D would be both low bias, low variance, right? If you guys see that. And so, it's a little bit confusing at first, but maybe just take a little while to kind of try and wrap your head around it, right? So how do we achieve both low bias and low variance, right? Because they're both errors, and we want to essentially minimize the errors that we have in our machine learning model, right? So to lower our bias, we could use a more complex model, right? We could use a model that assumes less assumptions about the structure of the data, right? And that can decrease our bias because essentially what's happening is that our model is more flexible, right, to the structure of the data. We can also provide the model with more features, right, because maybe there's information missing that we haven't provided yet to our model that the model could use. And to reduce variance, right, we can reduce the model complexity. We can make our model have more structural assumptions about the data so that it has less changes, right, when we're training our model on different data sets, right? We can also regularize our model. Essentially what we're doing is we're setting kind of some penalties to certain things in our model that kind of helps us limit what kind of hypothesis space we're looking for. Usually decreases the size of our hypothesis space, right? So like I said, achieving a low bias and a low variance is often not very achievable because of the bias-variance trade-off, right? So as it turns out, actually the total error of our machine learning model is equal to the bias squared plus the variance plus the irreducible error, right? So I explained what bias and variance errors are, right? But the irreducible error is essentially the error from randomness in our data, right? Which is the error from not so much the noise, but so much that the data itself is never going to be perfect, and you're always going to have that irreducible error that you can't lower, right? And so actually we see that our total error can never reach 0. And essentially what happens then is that we get this U shape for our total error, right? And since our total error is this U shape and really can never reach 0, we can have only kind of this best middle space that we say, right? Where both the bias and the variance kind of level out and they're in this kind of middle area, right? And we reduce the total error of our model. Otherwise, if we try to decrease our bias, right, what happens is that the variance increases and our total error goes up. Or if we try to minimize our variance too much, then we end up finding that our bias goes up and our total error goes up. So basically the intuition for this is that decreasing model complexity reduces the bias of our machine learning model, but at the same time increasing model complexity increases, or is this right? Decreasing model complexity reduces bias. Decreasing model reduces bias. No, this is wrong. Increasing model complexity reduces bias, but at the same time, increasing the model complexity increases variance, and the other way around. If you decrease model complexity, your variance drops, but at the same time, your bias increases, right? So your error will never really reach 0, and that's kind of the point where you have to make a trade-off with what kind of errors you want in your machine learning model, or where you're trying to essentially minimize the total error that you have, right? So now that we've kind of formalized some of these ideas a bit more about loss functions, hypothesis classes, right? Overfitting and underfitting and bias and variance, we're going to talk a little bit about linear regression, right? So linear regression, the definition for it is essentially what we're looking for is an algorithm for finding the best fitting hyperplane that predicts a target value, right? And usually it's a real number that we're trying to predict. We're trying to predict a real number given a set of one or more input variables. So what is a hyperplane here? So a hyperplane is essentially like a linear space in sort of 1 minus the dimension, n minus 1 dimensions of the dimension space you're talking about. So for example, if we're talking about a 2D plane, the hyperplane in that 2D plane would just be a line, right? Because a line has 1 dimension, your plane has 2 dimensions, right? If you're talking about a 3-dimensional space, right, then you would be talking about a 2D plane as your hyperplane, right? Because you have 3 dimensions, and so your hyperplane has 1 less dimension, so it has 2 dimensions, so it's a 2D plane in a 3-dimensional space, right? And it just generalizes this idea, right, of having a linear space in n minus 1 dimensions of the dimension space that you are considering, right? So remember that we have a data matrix X and the result vector Y, and we let Xi be the feature vector and Yi be the target value, for example, I, and we're trying to find this function, right, that maps the features of Xi to the target value we want, right? So we have these example data sets, right, that we have. We have X, Y, and W, which represent X is our data set, remember, Y is is the value of the house, and W are the weights, right? And so the model is defined by f theta of X, right, and you pass it in some set of features that you want to have it, and then it outputs basically a value, right? It's basically just linear weights, right? You multiply a weight by the first feature you give it, you multiply a weight for the second feature you give it, and so on, and you essentially get a scalar value, right, which is the value that you're trying to predict. And we also add the intercept, right, because we have to have the intercept for that, right? And so we can just basically rewrite it in the different forms of notation we want, right? So we can define it as we did in the previous lecture, or we can define it with the summation notation, or we can also define it with linear algebra. And we'll go through all of those today, how linear regression, how we actually solve for these optimal parameters, right? So it's an algorithm for finding the best fitting hyperplane, right? So to find the best fitting hyperplane, as we said before, which is basically finding the best fitting model, right? We want to define a loss function that outputs the error of our model when given the parameters, right? Which is the weight 1, weight 2, weight 3, all the way to weight m, and then the intercept, right? So previous lecture, we had mean absolute error. And so the mean absolute error was essentially just the average, right? As you can see, 1 over n over the summation of f theta of xi, which is essentially what our model is predicting, minus yi, which is the true value, right? So essentially all we're measuring is how far away are we from the actual value of the data in the real world, right? And then we're just averaging out how far we are, right? And that's the mean absolute error. Mean squared error is a little bit different, right? We do the same thing essentially, right? We're finding out the difference or the distance from our model to the actual true data, and then we just simply square it, right? And we divide it by n. So we're getting basically the average of the squares, remember, of the residuals. And so we define our optimal parameters essentially to be the parameters that minimize this loss function, right? Theta star, right, equals the weight 1 star, weight 2 star, so on, right? And we just define as the argmin, the arguments that minimize, right, the mean squared error, right? And so remember when we talked about convexity, right? We want our function to be convex because essentially that guarantees that the minimum of our function will always be a global minimum, or it might not be the unique global minimum, but it will always be the global minimum, right? And so the reason why we will want to choose mean squared error is because essentially it's always differentiable and it's also convex. And mean absolute error, I believe, is not differentiable. So mean squared error is just more mathematically convenient for us to use, and you'll see why shortly. Right? So now we've chosen the mean squared error, right? And this idea of linear regression using mean squared error as our loss function instead of mean absolute error, we call this ordinary least squares, right? So ordinary least squares is using linear regression specifically with the mean squared error loss function, right? So we explained why we choose mean squared error over mean absolute error. It's mathematically convenient for us to find the minimum of this loss function, right? So when doing linear regression with mean squared error, right, which is just ordinary least squares, we can actually get a closed form for the solution of this. And what that essentially means is that we can essentially represent the function, we can essentially represent the solution, the most optimal parameters for our model in a finite set of operations, right? So it's easy for us to see essentially how we can get the parameters here. So does anybody remember from calculus how we actually find the minimum to a function? Does anybody remember? Like optimization, Calc 1, I think you guys learned this. Yes?
Take the derivative and set it to 0?
Yes, take the derivative and set it to 0. Is there anything else maybe you want to expand on that?
Don't you also take the second derivative and see if it's positive, maybe?
Yeah, does anybody want to add, we're getting there. Anybody else want to add on to that? Yes?
Like if the function is convex, if it's not convex, it's very difficult to optimize those figures.
Yeah. But even if the function is not convex, how do we find the minimum, maximums, essentially? Yes?
Well, if the derivative before is negative and then the derivative after is positive, then it would be decreasing and increasing, so it'd be a negative.
Yeah.
It'd be a minimum.
Yeah, exactly, right? So essentially how we find the minimum to a function, right, is we take the derivatives of the function, right, and we set them equal to 0. And essentially when we're setting them equal to 0, that's when the slope is 0, right? So we define those as our critical points. And then as some previous people have mentioned, we essentially take the second order derivatives of that function. And essentially we like plot, you've done the chart, you have the plus minus, and you basically see if it goes from plus to minus. And you can essentially determine if it's a minimum, a maximum, and a saddle point essentially, right? So after we do that, it might be difficult to see, right? We have our minimums, we have our maximums, right? But right, we said the convexity matters for this because essentially after finding the critical points and then essentially restricting them to the minimums, right, we don't know if it's a global minimum. So the convexity essentially guarantees, right, that when we find any minimum, it'll be the global minimum. It might not be unique, but it'll be a global minimum, right? So that's why convexity matters for this loss function, right? So we're actually going to go through here kind of the math on how you find the best parameters here, right, shortly. Right, so we want to solve for our optimal parameters, right, with m equations and essentially m unknowns, right? So the process, right, is we have our loss function, right, which measures the error that our model is making, and we want to find the minimum of this function, right? So in calculus, right, as some people have said before, we would calculate the partial derivatives or the derivative if you just have one, you would set them to 0, and then you would solve that system of equations, and essentially what you would end up with is the minimum. And convex basically assures us that we'll have that global minimum here. Right, so you can see we're going to do it actually for our housing price estimator, right? So we have our function f theta of x, right, is the one that we're going to be trying to calculate the partial derivatives of, and we have our loss function, which is mean squared error, we're going to calculate the partial derivatives of our loss function, right, and we're going to set them to 0, right? So, but we're going to do this so we can find the optimal parameters from the function or the model in our first lecture, right? So first of all, let's rewrite our loss function in terms of our parameters, right? So first we have MSE, right? And we're just basically taking the average of the squares from the residuals, right? And on the right-hand side, you have the true data, right? So we can see that's kind of a straight plane, you know? So that's why we're going to say that, okay, maybe we can use linear regression for this, right? So we start off with our loss function, right? Essentially what we do is we just replace f theta of xi with our function from the last slide, right? Which is just w1, x1, I, which is I being the example that we're giving it, right? And we're just summing out all of these differences that we have from the actual data, which is yi, right? And we're squaring them, and we're just taking the average of the squares of the, essentially the squares of the residuals, right? So next, let's calculate our partial derivatives with respect to w1, w2, and b, right? And right at this point, if you guys don't understand the math, right, that's completely fine. This is definitely some stuff that, you know, you might have had a long time since you guys have done this last, right? So it's all right. Just see if you can kind of work your way through it and slowly understand it. Or maybe you guys are actually, you know, super smart and you understand completely everything that's going on, right? So we calculate our partial derivatives, right, with respect to w1, w2, oh, that's wrong, and b, right? And so what we're going to do is we're going to try and isolate for our variables here in a short while, and we're only going to do it for one of these equations to kind of see how we would actually do it, right? So we're going to do this with our first weight, right? So we have our function here for our partial derivative, right? And we set the partial derivative equal to 0, right? Because we want to find the critical points of our function, right? The points where the function, the slope is essentially, the gradient is essentially 0, right? So those can be minimums, maximums, and saddle points, right? If you remember from calculus. So we set them equal to 0. We set our partial derivative equal to 0, right? And so we can get rid of the 2 over n factor on the right-hand side because we just multiply 0 by n, so the n goes away, and then we can have the 1, we can multiply by 1 over 2 by also the 0, so the 2 goes away, right? And essentially, what we're left with is just essentially the summation of the weights multiplied by our inputs, right? And so we can expand out our summations, right? Because we're just adding stuff. So we can actually expand it out, right? All we do is we multiply the x1i in, and so essentially, and we distribute it across our components here, and we end up with this long-looking equation, 0 equals, you know, w1 times the summation of x1 I squared, right, and so on and so forth, right? And so we essentially do what we would do with any system of equations, right? We isolate for w1, right, which is our first unknown in this sense. And then once we've isolated for w1, we can do the same thing for w2 and b, right? And we can solve using any number of standard strategies that you would try to use to solve a system of equations, right? So you can do like substitution, right? Or the one where you cancel things out and stuff like that, right? So this is, you can see it's a little bit definitely, it's a little bit rough, right? And so at this point, we might say, okay, you know, solving the system of equations is quite difficult, and we only have 2 weights here, right? We only have 2 weights that correspond to 2 variables, right? Imagine if we wanted to do, let's say, like 10 variables or 20 variables. Well, then we have to solve for the partials for 20 equations, right? And then we have to solve the system of equation that has 20 equations, and then you see that can become quite burdensome, right? So what actually happens is that we can use linear algebra for this. And linear algebra is very well suited to solving for systems of linear equations, no matter how many equations we have, right? And so we can actually re-represent our problem using linear algebra notation, and that makes things a lot more compact, and it makes it a lot easier, right? So let's redefine our data set, right? The values, the true values, and our weights, right? So we're going to represent our data set x, and we're going to add that 1 there for the bias, and we're going to have our y vector, right, which is essentially just the values across. And if you remember, the row corresponds to the data example. So for example, x11 would be the square footage of the first house. x21 would be that second variable we defined also for the first house. And that 1 basically just represents the offset of our function, the y-intercept of our function, right? And so we have our y, which is just our list of values that the houses are, and we have our weights here, right? So all predictions can be written as y hat equals x dot product by w, right? So here xw is being performed, like I said, with the dot product operation. And so you can see kind of how we define the dot product here, right? We have xw, we've placed in our matrices, and you can see that essentially all we do is we multiply the value in the first column with the first weight, we multiply the value in the second column with the second weight, and we multiply the value in the third column with the third weight, which is b, right? And so we end up with this matrix, right? Essentially is just a column of values, a vector of values, right? And so you'll see it's actually very similar to what we were doing before, right? Of where we defined our function, right, to be w1 x1 plus w2 x2 plus b, right? It's essentially the same function. It's just that we are now storing all of the values that we have, right, from our data set. So y hat is the vector of all values that we are predicting with our model at this point. Right, so we have our predictions now of every single, all the predictions that our model is made, right? So now we're going to define our loss function using this new notation, right? So we have y hat, which is, right, the list of all predictions that our model has made, and we have the regular y, which is the actual true prices of all the houses, right? So we just essentially what we do is we minus the values, right, to get a new list, right? Which is essentially y hat minus y is just the list of the differences between from what our model has predicted and what are the true values of the house prices, right? And so we then find the square of the differences, right, by taking essentially what's called the Euclidean norm is denoted by those 2 bars on the left and right-hand side, right? So we can see here it's defined in very similar way, right, to our loss function. Actually, it's defined in the exact same way, right? It's just the summation of all the weights, right, of our function minus yi, right? So that's really all it is we're just summing up the differences, right? And we're just using a different notation to kind of help make this more compact for us to understand about and to view, right? And you can see y hat on the top right there, and you can see y, and we're just minusing the values, right, to see how far away our model's predictions are from the true values, right? And so, right, we can show it like this, and essentially what's happening here is we have our loss function, right? And we can take the Euclidean norm and we can expand it outwards. Essentially xw minus y, and remember xw is our predictions, and we just transpose and we multiply it by xw minus y. That's essentially the same thing as taking taking the difference, right, our model makes from the true values and then just squaring it, right? It's essentially the same thing we did before. So we now have defined our loss function in our new notation, right? So we try to find the gradient of this loss function that takes in our weights, we call them now, and we set it equal to the 0 vector, right? So now we're trying to essentially, the gradient is essentially the vector of partial derivatives of a function, right? So before we were trying to find the partial derivatives, right, with respect to w1, w2, and b. So it's essentially the same thing. We just have a list. We're just storing them in a list, essentially, right? We're storing a list of our partial derivatives in a vector. We're setting them all equal to a list of zeros, essentially, right, is what's going on here. So we can see that when we take the derivative, you actually might be able to kind of see what's going on, right? You take the derivative, so you have the I forgot, is it the chain rule? You bring out the 2, you bring the 2, right, to the front because it's the exponent, right? And then since x is essentially the constant that is multiplying w, and we're trying to find the gradient with respect to w, we bring out the x as well, right? So we get the 2x, right, multiplied by the xw minus y, right? Does everybody see that? You know, it's the derivative, right? And so now that we've set our gradient, right, which is the vector of partial derivatives, we've set it equal to 0, we can solve for our optimal parameters w, right? So all we essentially do is we do the same thing, is we expand out the 2x, right, with the xw minus y on the right-hand side, and then we can move over the x transpose xw, and we set it equal to x transpose y, and then essentially we just divide by it, right? So you can kind of see how the algebra works out here. And this represents actually our closed form solution for the best weights, right? Best weights in terms of mean squared error for linear regression, which is ordinary least squares, right? Does anybody have like any questions kind of about what's going on at this point? Any thoughts? All right. We'll move forward from here, right? Okay, so we've finally calculated the best weights, right, in terms of mean squared error for linear regression model, right? And so do we actually need this closed form solution, right? We actually don't, you know. Solving the partial derivatives and setting them equal to 0 and solving that system of linear equations can be very difficult, even with linear algebra, right? That's specifically designed to solve systems of linear equations. We can use, and we'll talk about this in future lectures, we can use an optimization technique called gradient descent, in which we essentially don't need to calculate these partial derivatives and try and find the critical points, right? And ensure that our function is convex, so we always can make sure that the minimum is the global minimum for our function and all of that fancy stuff. We can have a much more efficient way of finding the minimum of our loss function, right? So if there's anything you should take away from this, and it's not to get bogged down in the math, I kind of put the math up to show you just a little bit of how even the simplest model, right, linear regression, can actually be quite difficult to go through when you're trying to find the closed solution, right? If you guys didn't understand the math, that's completely fine. It's I would say it's quite difficult, to be honest. If you take the time to look through it, I think you guys will find, though, that you guys will actually be very capable in understanding exactly what's going on. Definitely don't doubt yourself when it comes to the math and machine learning. You guys will actually see that if you spend just even a few minutes trying to understand what's going on, you'll more than likely be able to get a good grasp of it. So don't be discouraged if you don't understand the math here. So there's some key takeaways, right, is that linear regression is an algorithm for solving the best fit for a linear relationship, right? And that's the key. It's a linear relationship. We're assuming that there is essentially in the data that there's linear weights we can multiply with the inputs to give us a value, right? And essentially it helps because it narrows down the hypothesis class, right? Which, remember, is the set of functions that we are looking in by assuming that the input-output relationship is linear, right? And so it may not necessarily be linear, at which point we're essentially just like, you know, wasting our time. But still, linear regression is great because it serves as a sort of baseline, right, for our models, right? If you have a deep neural network and you're training it to do regression, right, but you find that your linear regression model is actually, you know, just slightly below performance-wise in terms of your neural network, well, maybe you really don't need the neural network for your regression model. Maybe a linear regression is good enough. So it serves as a good baseline to figure out what kind of model complexity you need and gives you a good sense of where you are in the bias variance trade-off, right? Remember we talked about that. So, right, some advantages, it's that it's simple, it's fast, and it's interpretable, right? So we can see directly how the weights show how the inputs map to the outputs, remember? We can see like, oh, you know, if the square footage is like this much, then we're multiplying it by this way, and it shows the increase in the price of the house, right? Stuff like that. So that's definitely something missing in a lot of the more complicated or complex models, right? Interpretability. And some disadvantages, right, for linear regression is that it underfits usually, right? A lot of things in the world are not usually explained with the linear relationship, especially if you look to the extremes of certain things. Additionally, linear regression using mean squared error, so ordinary least squares, is very sensitive to outliers. And essentially the reason it's very sensitive to outliers is because if an outlier is very far away from what your model is predicting, you're essentially squaring that error, right? And then you're feeding it into your loss function, which really can change how your model predicts on new data, right? If you're changing the data set. So that's something that's not the best for sure. But that essentially closes off our lecture on linear regression, right? So just make sure you guys understand the key takeaways. I think is very important, and it's definitely one of the most fundamental models in machine learning, statistics, and data science. But yeah, thank you so much for your guys' time. Next lecture, we'll be talking about logistic regression. And yeah, so if you guys have any questions, just feel free and come up to ask me and stuff like that. And thank you so much. And here's the sign-in code.